In this module, we will introduce the notion of moments of a random variable. Many times it is convenient and indeed desirable to summarize the properties of a random variable in terms of some numbers. Moments of a random variable are essentially these numbers. The moments that we will talk about in this module are the mean value, the mean square value, and the variance, and the standard deviation, which is the square root of the variance, for a continuous random variable as well as for a discrete random variable. Let us first begin with a continuous random variable. So let x be a continuous random variable, then the nth moment of x is denoted by expectation. E denotes the expectation of x to the power n, defined as integration minus infinity to infinity small x to the power n into fxx dx, where the various symbols used are as follows. E denotes the expectation, capital X denotes the random variable, the symbol triangle equality we use for the definition. So defined as small x denotes the value that the random variable takes, and this fxx denotes the PDF, the probability density function of random variable x. We are interested in two special cases of this expression. Case 1, when n is equal to 1, the first moment of the random variable x. It is denoted as E of x equal to integration minus infinity to infinity x fxx dx. In this expression, the term E of x is, which is the first moment of x, is also called the mean value of x, or just the mean of x, or the average value of x, or just the expectation of x. And is also denoted by some other symbols as x bar or mu x or simply mu. All these notations are used interchangeably while describing the expectation or the first moment of x. Let us look at case 2. Case 2, when n is equal to 2. In this case, we get the second moment of the random variable x, denoted by E of x square, and is defined as integration minus infinity to infinity small x square into the PDF fxx dx. This second moment, of x denotes what we call the mean square value of x, the random variable x. And just as we define the moments of a random variable, we can also define the central moments of the random variable. So let us look at the central moment of the random variable x. And specifically, let us talk about the nth central moment of x. The nth central moment of random variable x is denoted by E, the expectation of capital X minus mu to the power n, and defined as integration minus infinity to infinity small x minus mu to the power n into the PDF fxx dx. Here again we are interested in two special cases, one when n is equal to 1 and then when n is equal to 2. So case 1, n is equal to 1. In this case we get E of x minus mu, the first central moment of x, which is by definition integration minus infinity to infinity x minus mu fxx dx, which can be rewritten as integration minus infinity to infinity small x fxx dx minus mu, which is a constant, times minus infinity to infinity integration fxx dx. Now in this, the first integral denotes the first moment E of x, or simply mu of the random variable x. The second integral denotes the total area under the PDF curve, which by definition is equal to 1. So we get the first central moment as mu minus mu, which is equal to 0. So we have an important observation here, that the first central moment of a random variable is always 0. So that's an important observation. Let us now look at the second case when n is equal to 2. When n is equal to 2, we get the second central moment denoted by E of x minus mu whole squared. The second central moment is also called the variance of x, denoted by VAR of x, or sigma subscript x squared, or just sigma squared. By definition, the second central moment becomes integration minus infinity to infinity small x minus mu squared into the PDF, which can be expanded as integration minus infinity to infinity x minus mu square is x square minus 2 mu x plus mu square into fxx dx, which can be separated into three integrals as integration minus infinity to infinity x square fxx dx minus 2 mu times integration minus infinity to infinity x fx x dx plus mu square times integration minus infinity to infinity fxx dx. Now here we can recognize the first integral as the second moment or the mean square value e of x square, or also denoted by x square bar. The second integral we recognize as the first moment e of x, or simply mu. The last integral is the total area under the PDF curve, which by definition is equal to 1. So the expression for variance can be simplified as e of x square minus 2 mu into mu plus mu square into 1, which is e of x square minus 2 mu square plus mu square, so minus mu square, alternatively expressed as e of x square minus mu is nothing but e of x, so e of x squared, or sometimes also written as x square bar minus x bar squared. So here we have a very important expression for the variance of x as the difference between the mean square value and the mean value squared. This is the mean square value and this is the mean value squared. The square root of this term, the variance of x, the sigma, which is the square root of the variance of x, is called the standard deviation of x. Which is a measure of the spread of the random variable around the mean value. So it's a measure of the spread. It signifies the spread of the random variable around the mean. And just as we have discussed the moments of a continuous random variable, we can talk about the moments of a discrete random variable. So let x be a discrete random variable now. In that case, we can similarly define the notions of moments and central moments as follows. The moments, the nth moment in general is written as e of x to the power n, defined as, now the integration becomes summation over all I xi, probability that x takes the value xi. This term, probability x equal to xi, is usually denoted by pxxi and is called the probability mass function, abbreviated as PMF. So just as for a continuous random variable we have a probability density function, for a discrete random variable we have a probability mass function. One important difference we must keep in mind, that whereas the probability density function is not a probability, the probability mass function is a probability. So we can make a note of it on the side, that PDF is not a probability, but PMF is a probability. So keeping this in mind, the nth moment, let us write down once again, is written as e of x to the power n, defined as summation over all I xi px xi. So this is the definition. The two special cases which we are interested in, when n is equal to 1, we get E of x, which is equal to summation over all I. I should make a correction here. The nth moment is summation over all I xi to the power n px xi, and when n is equal to 1, it becomes summation over all I xi px xi, also called x bar or mu x or mu. When n is equal to 2, we get E of x square, the second moment, which is also denoted by x square bar, as summation over all I xi squared px xi. We can also have the central moments, the nth central moment defined as E of x minus mu to the power n, that denotes the nth central moment of the discrete random variable x. It is defined as summation over all I xi minus mu to the power n px xi. When n is equal to 1, we get the first central moment Ex minus mu, which becomes summation over all I xi minus mu px xi. When we expand it, we get summation over all I xi px xi minus mu times summation over all I px xi. The first term here is the first moment, which is simply mu this term is mu, and the second summation here is the total probability, which must be equal to 1. So we get here mu minus mu, which is equal to 0. So as before, the first central moment of a random variable, whether continuous or discrete, is 0. Let us now look at the second central moment when n is equal to 2. So we have Ex minus mu to the power 2, which becomes summation over all I xi minus mu squared into px xi, which when we expand, we get xi square minus 2 mu xi plus mu squared into px xi. Now this can be written in three separate summations as summation over all I xi squared px xi minus 2 mu times summation over all I xi px xi, and finally plus mu square summation over all I px xi. And we can recognize these three different summations as the first one as the second moment E of x squared, or simply x square bar, the second summation as the first moment E of x or mu, and the last summation we identify as the total probability, which is equal to 1, and therefore the second central moment can be written as E of x square minus 2 mu into mu plus mu square into 1, which is equal to E of x square minus mu square, or which can be written as E of x square minus E of x whole square. or in other notations x square bar minus x bar squared. So the expression is same as that we had obtained for the case of a continuous random variable. So in this module we looked at the moments of a random variable. Specifically, we concentrated on the mean value, the mean square value, and the variance, and also the standard deviation, which is the square root of the variance and which denotes the spread of the random variable around the mean value. So that's all for this module. Thank you.